Dear students, welcome back to another video lecture on the course Signals and Systems with course code 18EC45. In the previous video lecture, we completed our study on properties of the system. There are 6 properties to the system, and the first property we studied was memory property. A system can be memory system or it can be a memoryless system. A system is said to be memory system if the output of the system depends on present input as well as past input to the system. And a system is said to be memoryless if the present instant output of the system depends only on the present input to the system. And the second property we studied was time invariance. A system can be time varying or time invariant. A system is said to be time invariant if input signal is shifted by some quantity, either the signal is time delayed or time advanced, then it should introduce the same time delay or advance in the output signal as well. If this is the case, then the system is said to be time invariant system. And the third property we studied was causality. A system can be causal system or a non-causal system. A system is said to be causal system if the output of the system depends on present input, past input, and sometimes past outputs of the system. And if the system's output depends on present input, past input, as well as some future values of the input, then a system is said to be non-causal system, which are generally non-realizable. Then we studied the property of stability. A system can be stable system or an unstable system. With respect to input and output signal, a system is said to be stable system for if a bonded input produces the bonded output, then a system is said to be stable system, else a system is said to be unstable system. Then we studied invertibility. A system can be invertible system or a non-invertible system. A system is said to be invertible if we can recover the input signal back from the output signal. Meaning, if we apply output of a system to one more system as an input, and from that system, if we are able to recover the input of the first system back, then a system is said to be invertible system. And the system which gives us the original input signal as an output is said to be inverse system, inverse of the invertible system. And lastly we studied linear property. A system can be linear or a system can be non-linear. Now for a system to be linear, it should be satisfying two conditions: principle of homogeneity and superposition. If we form a composite signal, then the output to the composite signal should be addition of the individual components to the input system input. And homogeneity means if signal is scaled by some factor, then the output should also be scaled by the same factor. If these two conditions are satisfied, then only a system is said to be linear system. If either one of these fail, then a system is said to be non-linear system. In this lecture, we will extend our study to a particular class of systems called as linear time invariant systems. Now, out of these 6 properties we studied, we'll consider only 2 properties which are very important: linear as well as time invariance. Now, these linear time invariant systems, they can be stable system or unstable system. They can be causal system or non-causal system. They can be invertible or non-invertible. The rest 4 properties will not worry about them. But the major 2 properties that we'll be considering is a system has to be linear as well as it has to be time invariant. We'll be considering these 2 properties in the system and we'll study these linear time invariant systems. These class of systems, linear time invariant systems, or generally referred to as LTI systems, are very important because most of the useful systems in the nature can be approximated by linear time invariant systems. Generally, the systems that we design are non-linear as well as time varying. So these are the LTI systems are the ideal case. First, we'll design linear as well as time invariant system. We'll verify the response of these systems for various input, and later all those non-linearities and time varying factors can be taken into consideration to design a real-time system. So linear time invariant systems are the ideal case because most of the useful systems can be approximated into linear to have linearity property as well as time invariance property. Now for these systems, we'll consider some arbitrary input signal x of t, and in module 1, as part of one section, we studied the basic signals and functions that are available to us. We studied the mathematical expression, we understood different properties of those basic signals. We'll be using them here. If any arbitrary signal, let it be in continuous time domain or in discrete time domain, if we can decompose those signals in terms of large number of simpler components or basic components. Now, some of the basic signals we studied are exponential signals, ramp signal, rectangular function, unit step function, unit impulse function. We studied different basic signals in module 1. Now, out of these basic signals, any arbitrary continuous time signal or discrete time signal, if we can decompose any arbitrary signal into one of these basic signals, then the signal, continuous time signal or discrete time signal x of t or x of n, can be weaved as superposition of those basic components. It is like forming a composite signal by adding different components, and each of those components will be a basic signal or the basic component, and each component will be of the same function. If we are able to form the composite signal, then that composite signal x of t can be represented as superposition of these basic components given by summation over I ai xi of t, where xi of t are the basic components and ai is the scaling factor, amplitude of those basic components at particular instant of time. Then if we want to record the output for such input, if the system is linear time invariant, then all we need to do is find the output from LTI system for each of these input components, each of these simpler signals xi of t. Now, because the system is linear as well as time invariant, we'll look into the time invariant property in a couple of minutes. If the system is linear, then the output from the system, because of this linearity property, that is superposition and homogeneity, the output from that linear system should be y of t equals to summation I ai yi of t. Now yi of t will be the output due to the simpler components as an input to the system, and ai of t will be the multiplication factor due to homogeneity, and output due to each of these simpler components will be accumulated together in terms of summation, which is superposition. Now this is the reason why linear time invariant systems are very simple to analyze. Now I said we'll be decomposing the continuous time signal or discrete time signal into one basic signal or one basic function, and we'll choose unit impulse function to decompose any arbitrary signal into. Because we know the properties of unit impulse function, and unit impulse function is the most important and most relevant one to decompose any arbitrary signal into. We'll look into how we can decompose that, but we'll be decomposing signal x of t into only one elementary signal in case of continuous time or discrete time. In case of continuous time, we'll decompose x of t into delta t, which is unit impulse function in continuous time. And in case of discrete time signal, x of n will be decomposed into discrete time unit impulse represented by delta n. For example, if we consider an continuous time system and if we apply delta t as an input to it, then we'll get some response from that linear time invariant system. Let us call it as h of t. Now this h of t refers to unit impulse response, or sometimes it is also called as unit sample response. Unit impulse response is the output of linear time invariant system if the input to the system is unit impulse function delta t. If delta t is the input, output will be h of t, which is referred to as unit impulse response because of unit impulse function as an input. If we know the unit impulse response or h of t of any linear time invariant system, then we can easily find out the output from that linear time invariant system, which will be y of t for any arbitrary input x of t, provided we should be knowing the impulse response or h of t for the LTI system, and we'll get unit impulse response or h of t only if the system is linear as well as time invariant. And in the similar manner, the same explanation can be extended to discrete time signals and systems as well. If we consider a discrete time system and if we apply delta n, discrete time unit impulse function, as an input, then output from LTI system will be calling it as h of n, which will be the discrete time unit impulse response of the system. And again, if we know the unit impulse response or unit sample response for an LTI system, output of that system for any arbitrary input x of n can be obtained, because x of n can be decomposed into simpler functions, superposition of simpler functions, and those simpler functions will be considering is unit impulse function here. And all of these concepts is valid only if we can decompose x of t or x of n in general, any signal, in terms of delta t or delta n, else the whole concept is invalid. Now, how do we decompose any arbitrary signal into simpler components, and how superposition will give us the signal under consideration? We'll look into that. For that, we'll consider a discrete time signal, 5-point discrete time signal x of n, as shown in the figure. It is 5-point discrete time sequence because there are 5 samples, and the discrete time sequence is defined between -2 and +2. At -2, the amplitude is half. At -1, the amplitude is 1. At n equals to 0, amplitude is 0. At n equals to 1, amplitude is -1. And at n equals to 2, amplitude is +half. Now, how can we look, or how can we decompose this discrete time signal x of n into simpler components? Now, each of these samples in the discrete time signal will be looked upon as an impulse function, because we know the definition for unit impulse function in discrete time domain. At n equals to 0, we'll be having an delta function, which will be represented by delta n. At n equals to 1, it will be an time shifted unit impulse function, which can be represented as delta n minus 1. And likewise, at n equals to -1, it will be time advanced unit impulse function, which can be represented as delta n plus 1. And likewise, at n equals to 2, at that position, for n equals to 2, the sample can be looked upon as time delayed unit impulse function represented by delta n minus 2. And the amplitude values will be multiplied to it. So x of n can be rewritten. So x of n can be rewritten as superposition of simpler functions. For the given example as x of n equals to, at n equals to -2, there is a sample present, and in terms of impulse, it will be represented as delta n plus 2 because the sample is presented. If you look at it as an impulse function, then it is present at -2. It's an time advance operation as we studied in module 1. So delta n plus 2 will be the position of this impulse function, and the amplitude of that impulse function is 1 by 2. So 1 by 2 will be multiplied to the position where the impulse is present. So together it will be written as 1 by 2 delta n plus 2. And this will be followed for all the other samples in the discrete time sequence. At n equals to -1, delta function will be represented as delta n plus 1, and amplitude for that will be 1. At n equals to 0, there is no function present, there is no amplitude present, so it will be delta n multiplied by 0, which will be 0. So we'll omit writing that. And at n equals to +1, delta function will be represented by delta n minus 1. Because the amplitude is -1 there, so -1 will be multiplied outside, so it will be -1 delta n minus 1. And lastly, at n equals to 2, impulse function will be represented by delta n minus 2, and the amplitude is 1 by 2. So in this way, we can decompose given discrete time signal into superposition of basic functions, and the basic function we consider to represent a signal with here is unit impulse function. Now if we know the response of a linear time invariant system to delta n, then due to time invariance property, we'll be knowing the response to all the components of the time shifted unit impulse functions, which will be given as, if delta n is the input to LTI system, the output of that LTI system will be represented by h of n, so which is represented by delta n yields h of n. Because of time invariance property of the system, if this impulse is shifted, either it is time delayed or advanced, which will be represented by delta n minus n naught. And if this is the input to LTI system, because of this time invariance property, the output has to be h of n minus n naught. Impulse response will be shifted by the same amount of time as that the input was shifted. So in general, if you combine all the terms of the delta function in terms of summation, so any arbitrary discrete time signal x of n will be given by summation k minus infinity to plus infinity x of k delta n minus k. Delta n minus k are the impulse function and time shifted impulse functions, and x of k are the amplitudes of these delta functions present at those instants of time. So any arbitrary signal x of n can be decomposed or can be represented into simpler functions as summation k minus infinity to plus infinity x of k delta n minus k. Now if this is the input to a linear time invariant system, then what will be the output from that linear time invariant system? Because I said if we know the impulse response of the system, then we can know the output of that LTI system for any arbitrary input x of n. Now to determine that, let us follow a procedure, simple plus procedure. Again, let's consider the input output relation with respect to impulse. If delta n is the input to LTI system, then impulse response h of n will be the output from that LTI system. And because of time invariance property, if this impulse function is time shifted, let us represent that time shifting operation by delta n minus k. If this is the input to LTI system, because of time invariance property, the impulse response, the output should also be shifted, which will be represented by h of n minus k. Now linearity will come into picture. For linearity, there are two principles, homogeneity and superposition. And because of homogeneity, if these time shifted impulses are multiplied by some factor x of k, then the output of LTI system, which is the impulse response, time shifted impulse response, h of n minus k, will also be multiplied by the same factor x of k. And because of superposition, if we accumulate all the terms in terms of summation, then output terms will also be accumulated. They'll also be superimposed, given by summation k minus infinity to plus infinity x of k delta n minus k will result into summation k minus infinity to plus infinity x of k h of n minus k. So summation in the left hand side is the decomposed input signal, which can be written as x of n. If this is the input to LTI system, then the summation on the right hand side has to be the output of the LTI system for the applied input x of n, which can be represented as y of n. In other words, output y of n of a linear time invariant discrete time system to any arbitrary input x of n can be written as y of n equals to summation k minus infinity to plus infinity x of k h of n minus k. And this summation is called as convolution summation, or in simple terms, it is also referred to as convolution sum. And this equation is very, very important. As you might have already known, this equation will come in lot of the other concepts that we have studied earlier. For example, in module 3, we encountered this convolution summation. In module 4 also, we encountered this convolution summation. In Z transform, in module 5 also, we get this convolution summation. So this is a very important operation. And it is the only operation through which we can obtain the output of discrete linear time invariant system for any arbitrary input x of n. And this is called as convolution summation. You need to remember this equation by some means. And h of n is the unit impulse response, or sometimes it is also referred to as unit sample response. It is the response of the LTI system when unit impulse function is applied as an input to it. Now this summation has three operations or three steps. First, we need to choose a value of n which will be equals to k. Then we'll shift the impulse response to obtain h of n minus k. And then we'll multiply two samples, x of k and h of n minus k for particular value of k, and then sum them up over all possible values of k. And this operation is called as convolution or linear convolution, and it is represented by y of n equals to summation k minus infinity to plus infinity x of k h of n minus k, where x of k is the input to the linear time invariant system and h of n minus k are the time shifted impulse response of the same linear time invariant system. And the operator used to represent the convolution is asterisk. So the above summation gives us the convolution between the input sequence and impulse response of the LTI system. Using convolution operator, it can be represented by y of n equals to x of n asterisk h of n, where asterisk represents the convolution operator. And if in the above summation, if we substitute n minus k equals to r, then k will be equals to n minus r. By substituting this in the convolution summation, we'll get y of n equals to summation r minus infinity to plus infinity x of n minus r h of r. If you compare equation 1 and 2, they are similar. It means either we can shift the impulse response and then multiply it with the input sequence, or we can shift the input sequence and then we multiply it with the impulse response. Both will give us the same result, y of n. It means convolution operation is commutative. Because of this second summation, we can write y of n as h of n convolution with x of n. Either you convolve input with impulse response or convolve impulse response with input, both will result into the same output. So the operation of convolution is commutative. In the following section, we'll be looking into some of the properties of convolution sum or convolution summation. As we had been through, convolution summation is commutative. Either you convolve input signal with impulse response or convolve impulse response with input signal. Both will result into same output. So the statement for commutative property is x of n convolved with h of n will be equals to h of n convolved with x of n. And in terms of convolution summation, x of n convolved with h of n will be given as summation k minus infinity to plus infinity x of k h of n minus k. Like we did earlier, if we substitute n minus k equals to r, we get summation r minus infinity to plus infinity x of n minus r h of r, where r is a dummy variable. It can be replaced with k because both take integer values. So we can rewrite the summation in terms of k, which is nothing but h of n convolved with x of n. So convolution is commutative. Convolution is also associative. If we have two systems connected in series, let the impulse response of first system be h1 of n and impulse response of second system be h2 of n. If we apply input x of n to the first system, then the output of first system will be x of n convolved with the impulse response h1 of n, which will be the input to the second system. So the entire input to the second system, which is convolution between the input x of n and the impulse response h1 of n, will be convolved with the impulse response of the second system, which will be represented by h2 of n. Or we can combine both the LTI systems with different impulse responses and apply input x of n to it, so that the output will be same. Proof of the associative property is very simple. We'll consider x of n convolved with h1 of n as f1 of n and h1 of n convolution with h2 of n as f2 of n. We'll substitute these in the above equation and we'll simplify. So f1 of n will be summation k minus infinity to plus infinity x of k h1 of n minus k. So x of n convolution with h1 of n whole convolution with h2 of n can be written as f1 of n convolution with h2 of n. In terms of convolution summation, it will be summation m minus infinity to plus infinity f1 of m h2 of n minus m. In place of f1 of m, we'll substitute the convolution above for x and h1. And by simplifying, by substituting r equals to m minus k and rearranging the terms, we'll get summation k minus infinity to plus infinity x of n of summation m minus infinity to plus infinity h1 of r h2 of n minus k minus r. We know the definition for f2 of n, which we defined for convolution between both the impulse responses h1 and h2. If we shift it, if we introduce n minus k, then the second term will be h2 of n minus k minus r. So the entire term will be summation k minus infinity to plus infinity x of k f2 of n minus k, which is convolution between x of n and f2 of n. So convolution is associative. Along with commutative and associative property, convolution is distributive as well. X of n convolved with h1 of n plus h2 of n will be equals to x of n convolved with h1 of n plus x of n convolved with h2 of n. It means if we have two systems with impulse response h1 and h2 which are connected in parallel, if we apply a common input x of n to both of those, then the output will be addition of the output of first system and second system, which will be given by x of n convolution with h of n and x of n convolution with h2 of n. Proof is very simple. We'll consider the left hand side and write the convolution summation for it, which will be x of k h1 of n minus k plus h2 of n minus k. We'll divide the summation between both the terms, and each of those summations, they represent the convolution of the input with the respective impulse response with h1 and h2. So convolution is distributive as well. And the fourth property is the identity sequence for the convolution operator is delta n. It means if the input signal is convolved with delta n, or impulse function is convolved with input signal x of n, the result will be x of n itself, the original input signal x of n itself. So delta n, unit impulse function, is the identity sequence for the convolution. The fifth property is the convolution of the delayed unit impulse sequence with x of n, given by x of n delayed convolved with delayed impulse delta n minus k. Then the output will be, the sequence will be delayed, x of n minus k. And the last property is convolution of two delayed unit impulse sequences delta n minus m and delta n minus k will result into an impulse function which will be delayed by taking into account both the impulses. Delta n minus k convolution with delta n minus m will be equals to delta n minus of m plus k, where m and k are the time shift of each of the impulses. I hope you all understood the concept of linear time invariant systems, impulse response, and most importantly the convolution summation. If you have any doubts, you can contact me. Thank you all.